For each degree sequence below, decide whether it must always, must never, or could possibly be a degree sequence for a tree. Justify your answers. A tree is a connected graph containing no cycles. For any tree, the number of edges E is equal to the number of vertices V minus 1. To help us answer these questions, we'll also be using the handshake lemma, which states, in any graph, the sum of the degrees of vertices in the graph is always twice the number of edges. We will use a degree sequence to determine the number of vertices and the number of edges, and then check the equation E equals V minus 1. If it's false, we know the degree sequence can never be a tree. If it's true, we'll have to check some graphs to see whether it represents a tree sometimes or always. And we are using the definition of a simple graph, meaning no two vertices can be connected by more than one edge, and no edge can be connected to just one vertex. We are not considering multigraphs in this exercise. So for part A, there are 5 degrees in the degree sequence, which indicates V, the number of vertices, is equal to 5. Next, we determine the degree sum, which is 12. This is equal to twice the number of edges. To find the number of edges, we divide by 2. E, the number of edges, is equal to 6. And now we check the equation E equals V minus 1. In this case, we have 6 equals 5 minus 1, which is not true. This indicates the degree sequence can never represent a tree. And now let's take a look at B. Notice B has 6 degrees in the degree sequence. This indicates there are 6 vertices. The degree sum is 10. 10 divided by 2 is 5, indicating the graph has 5 edges. Checking the equation E equals V minus 1, we have 5 equals 6 minus 1, which is true, which indicates the degree sequence could possibly be for a tree, but we don't know if it's always going to be a tree. We need to check some graphs. Let's first sketch a graph that's a tree with the given degree sequence. And sketching these graphs can be a little bit challenging. We know we have to have 6 vertices, and the degree sequence must be 3, 2, 2, 1, 1, 1. Let's build the graph in pieces. If we sketch 4 vertices and sketch edges in this manner, we have 1 vertex with degree 3 and 3 with degree 1. And we still have to have 2 more vertices. So if we sketch a vertex here, and then sketch edges here and here, I think we have the correct degree sequence, and we also have a tree. The degree sequence is 3, 2, 2, 1, 1, 1, which is the correct degree sequence. The graph is connected and does not have any cycles. We have a tree. So now we need to see if we can sketch a graph with the same degree sequence that is not a tree, and if we can, the degree sequence could possibly be for a tree, but not always be a tree. So again, this can be a little bit tricky. I'm going to go ahead and start in the same way. Connect these. And then to get 2 vertices with degree 2, I'm going to go ahead and connect these two. Let's check the degrees. We have 3, 2, 2, 1. We need 2 more vertices, both with degree 1, which we can form if we have a disconnected graph that looks like this. So we do have the correct degree sequence, 3, 2, 2, 1, 1, 1. However, the graph is disconnected and there's a cycle, indicating the graph is not a tree. So for this degree sequence, the graph could be a tree or it could not be a tree. Our final conclusion is the degree sequence could possibly be a tree. And now let's take a look at C. There are 6 degrees in the degree sequence. Number of vertices is 6. The degree sum is equal to 12, which indicates there are 12 divided by 2 or 6 edges. Again, we check the equation E equals V minus 1, which in this case is false. This indicates the degree sequence can never be a tree. And now let's check D. There are 8 degrees in the sequence, indicating there are 8 vertices. The degree sum is 14, indicating there are 14 divided by 2 or 7 edges. Now we check the equation E equals V minus 1, which in this case is true. 7 equals 8 minus 1. So because the equation is true, we now have to check some graphs. Let's first form a graph that is a tree using the degree sequence. So I'm going to start with 4 vertices and connect them using edges in this way. Right now we have degrees 3, 1, 1, 1. I'm going to sketch this again on the right. Right now, notice how the graph is disconnected, and the degrees are 3, 3, 1, 1, 1, 1, 1, 1. Notice how we have the 6 1s, but we have 2 degree 3s, not 2 degree 4s. We can make these degree 4s by connecting the 2 degree 3 vertices. And notice now we do have the correct degree sequence. We have 4, 4, 1, 1, 1, 1, 1, 1. The graph is connected and there are no cycles. This is a tree using the given degree sequence. So now the question becomes, can we form a different graph with the same degree sequence that is not a tree? If we can't, then the answer is the degree sequence will always be a tree. If we can, then it could possibly be a tree. In this case, we're not going to be able to sketch a graph with the given degree sequence using the definition of a graph above where no multiple edges are allowed between 2 vertices and no edges can connect to just one vertex, and therefore this degree sequence always represents a tree. And I would encourage you to try a few graphs to convince yourself it's not possible. I hope you found this helpful.